All right. Good afternoon. Um, Today, just kind of picking up with equations that consist of complex roots. We're going to make a little bit of a segue thereafter into equations that have both types of roots, real and complex. And just kind of going back to what we have from page 81 and looking at the various types of quadratic equations involved. And for what we have in the case of number 57, okay, this time we're looking at solving for the variable u, whereupon we have 4u squared plus 64 is equal to 0. And looking at solving for this equation, okay, so I have 4u squared plus 64 is equal to 0, and I have only one term in the variable u with 4u squared. And in terms of getting this term by itself, I can undo the addition by 64 by taking 64 away from both sides. So we have in the rewrite, I have 4u squared is equal to negative 64, and then isolating u squared, we have upon division by 4, so we're going to have the left hand side to become u squared, and we have u squared equal to negative 64 over 4, which will be negative 16. And we have in the follow through upon utilizing the square root property of equality, this time working with the letter u. So I'm transforming u squared to u, whereas on the right I'm going from negative 16 to plus or minus the square root of negative 16. So we have for u itself, okay, we'll have a couple of complex roots. Okay, now we have plus or minus, and the square root of 16 is 4, but now the square root of negative 16 goes to 4i. So for the variable u, okay, we have two additive inverse complex roots with 4i as well as minus 4i. Okay. Now for the next item, and we have with number 58. Now the nature of the problem is very much the same. This time we're going from the letter u to the letter p. Once again, we're going to have just a single term in the variable we're solving for. And this time we have 8p squared, and we have plus 72 equals 0, and getting the p squared term by itself, so I can undo the addition by 72 upon subtracting. And so we're going to have 8p squared is equal to negative 72. And we have with division by 8, okay, so you have that p squared is equal to negative 9. And once again, utilizing what we have with the square root property of equality. So we have p squared goes to p, and we have that set equal to plus or minus, okay, the square root of negative 9. And in this case, we have p is going to go to plus or minus, where we have the square root of negative 9 goes to 3i. And just like what we have with u, we have in p, okay, complex roots that are additive inverses of each other. So again, we have 3i and negative 3i. Okay, so we have with these quadratic equations, we had only one single variable term. Now for the next item, okay, we're going to have two terms. And this time we're looking at solving for the letter t. And in this one, okay, we have in 61, Okay, we have t squared minus 8t is equal to negative 24. And then looking at solving for t. So I have a quadratic equation that consists of two variable terms with t squared and minus 8t. And if I write this equation in standard format, that is set it up as a trinomial, set equal to 0. So if I add 24 to both sides, so we're going to have in the rewrite, we will have t squared minus 8 times t plus 24 is equal to 0. And now for what we have with this particular trinomial, I cannot factor into real integer coefficients, because if I think of like trying to factor by grouping, but here you have 1 times 24 is 24, but there are no factors of 24 that will add up to negative 8. You might think of like negative 24, negative 1. Those add up to negative 25. And then you might try negative 12 and negative 2. Well, they multiply out to 24. They add up to negative 14. And then we have the next possible combination, which would be negative 6 or negative 8 and negative 3. Those add up to negative 11. And you have like negative 6 and negative 4. However, those add up to negative 10. But there's no combination that will add up to negative 8. So we can follow through, okay, as a bit of a recourse through utilizing the quadratic formula. Okay, so we have with t squared, again, you read this as 1t squared. So we have that a is equal to 1. And we have for minus 8t. Okay, so we have b is equal to negative 8. And we have with plus 24. Okay, so you have that c is equal to 24. And taking what we have now and solving for t. So again, we have a different variable we're solving for, but again, we're using the same ABC expressions. So we have here, so for negative b, okay, so again, this is going to translate out to the opposite sign of negative 8. And you have plus or minus the square root. Okay, now we have a b squared. So we have the square of negative 8. And you have minus 4 AC. So you have minus 4 times 1 times 24. We have all over 2a. Okay, so you have 2 times 1. Okay. Now for the activity going on inside the radical. Okay, so you have within. Now the square of negative 8 is going to become negative 8 times negative 8, which is positive 64. Now we have with negative 4 times 1, you have negative 4. Negative 4 times 24 becomes negative 96. And 64 minus 96 becomes minus 32. And if I take the square root of the difference, so you have the square root of negative 32. So you have the square root of 32 times I. And lowering, okay, so the highest perfect square divisible into 32 is going to be 16. So the square root of 32, you have square root of 16 times the square root of 2, and then we have the I to follow. And for the reduced radical, we have 4 times, okay, the square root of 2 times I. Okay, so we have looking at what we have in the putback. So we have, so you have opposite sign of negative 8, so this will be a positive 8. And you have plus or minus, and again, the radical expression reduces to 4 times the square root of 2 times I, and 2 times 1 is 2. And notice we have even valued leading coefficients. Okay. And we have dividing by 2 in the compact notation. So 8 over 2 goes to 4. And plus or minus, and 2 would go into 4 square root of 2i, which would be 2 times the square root of 2i. So this will be your compact notation. And again, if you draw out separately, we're going to have 4 plus 2 times the square root of 2i, and also 4 minus 2 times the square root of 2 times I. I think it is, but I'm not 100% sure. Okay. Now, in the case of 68, okay, so we have, in this problem, so we have m times, okay, and we have the quantity of m plus 10 is equal to negative 34. And again, just with the setup, one might be prone to setting m and m plus 10 each equal to negative 34. But let me mention, if you're thinking of using the zero product property, the number on the right cannot be a positive or a negative. It must be 0. So I cannot work with m or m plus 10 alone. So what I'm going to have to do here is to untangle what is present in 68 and remove the parentheses. So I'm going to multiply the expressions I have at m. So we're distributing m over the quantity of m plus 10. Okay, so this will be m squared plus 10m is equal to negative 34. Okay, so we have another quadratic equation, this time in the variable m, and it is not yet in standard form. So if I move the 34 over, okay, so we're going to have here, we have m squared plus 10m plus 34 is equal to 0. Alright, and so we have, in the case of this trinomial, now this one cannot be factored into real valued integer coefficients either. There are no factors of 34 that will add up to 10 that are real integers. You might think of like 1 and 34, 2 and 17, and those add up to 35 and 19 respectively, but not 10. And so once again, looking at the quadratic formula as a recourse, you can see I have 1m squared. So this leaves that a is equal to 1, and then we have plus 10m. So this will signal that b is equal to 10, and then we have c is equal to 34. And taking what we have with m, okay, and once again setting equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So for negative b, we have minus 10, and plus or minus, okay, the square root. Okay, so you have b squared, so this would be 10 squared. And you got minus 4ac, so you have minus 4 times 1 times 34. We have all over 2a, so we have 2 times 1. And once again, looking at what we have inside the radical. So we have 10 squared, this will be 100. And then we have minus 4 times 1 is negative 4. Negative 4 times 34 is going to be a negative 136. So the difference here is going to be a minus 36. And for the square root of negative 36, Okay, so I have square root of 36i, or right away you can go ahead and express as 6i. And so for what we will have in the follow through, okay, so we have negative 10 plus or minus 6i all over 2, and just reducing. Okay, so you have negative 10 divided by 2, so this would be negative 5, and plus or minus 6i over 2, okay, and 6 divided by 2 is going to be 3, so we have negative 5 plus or minus 3i, and just for the expanded notation, so we have negative 5 plus 3i, also have negative 5 minus 3i. All right, now for what we have in the case of still, so far we have had exclusively complex roots, and just sort of maintaining the course right now, and there's going to be a little bit of a change up shortly. Now for what we have in the case of 71, again, so we're going back to where we have a single variable term, kind of like what we had earlier with numbers 57 and 58. Okay, just a single term in the variable we're looking at solving for. And again, you have a constant added, and again the equation is set equal to 0. So the setup in 71, very much like numbers 57 and 58. And just like before, I can isolate the variable term by undoing the addition that is alongside it. So in this case, if I move the 49 over, so I'm going to have that 9x squared is equal to negative 49, and then expressing what we have here in terms of x squared. So if I divide by 9, okay, so we had the x squared is equal to negative 49 ninths. And once again, utilizing the square root property of equality, so I have x equal to plus or minus the square root of negative 49 ninths. Okay, so you have plus or minus the square root of 49 ninths I, and the numerator and denominator are both perfect square terms. So in this case, the square root of 49 is 7, the square root of 9 is 3, so the square root of 49 ninths is going to be 7/3. So we have yet another two complex solutions with positive and negative 7/3 of I. Okay, so again we had yet another equation leading up to complex roots in the solution. We have among the varieties, okay, we'll have what will be referred to as equations quadratic in form. Okay. Not quadratic equations per se, but they will likely be of other degrees, okay? And, okay, now for equations quadratic in form, okay, without giving a very long definition, we say that for equations quadratic in form, we say that we have equations where they will not always be displayed as such, but we have equations where if there are two variable terms, say we have, if there are two terms in the dependent variable, but you might have like other categories like differences of squares where you would not have two terms in the variable. But if there are two terms in the dependent variable, then the higher order term will be twice the degree of the lower order term. Now place emphasis on this in case you have twice the degree. And just as samples of equations that are quadratic in form. Okay, now not looking at solving, but just in terms of just showing how an equation can be quadratic in form. And we can say that we have, first of all, we can say that we have x to the fourth plus 19x squared plus 1 is equal to 0. Okay. So you have x to the fourth plus 19x squared plus 1 is equal to 0. And we have two terms in the variable x. Okay, higher order we have at 4, lower order we have at 2. And guess what? We have a 4 to 2 ratio. 4 over 2 is equal to 2. And we can say that this equation is going to be quadratic in x squared. In other words, quadratic in the lower order variable factor. And if we have, let's say, something like 3x to the sixth minus 97 x cubed plus 4 is equal to 0. Okay, if you notice between the higher and the lower order terms in x, okay, we have higher order is at 6, lower order we have at 3. And again, the higher order in x is twice the degree of what we have in the lower. So you have a 2 to 1 ratio. And this equation is going to be said to be quadratic in x cubed and let's say that if we have another situation, and we'll say that we have, say, a 5x minus the square root of x plus 88 is equal to 0. Okay, now we have 5x minus the square root of x plus 88 is equal to 0. And another way you could express this, remember, you have 5x. Now the square root of x, remember, with square roots, okay, the hidden index number is going to be 2. So you have like the second root of x to the first. So as a non-integer exponent, okay, the square root of x is going to be x to the 1/2. And guess what? Comparing the degrees, so 5x, you have x to be a first order. And we have 1 to 1/2. And guess what? 1 divided by 1/2. That's going to come out to a 2 to 1 ratio, which is going to go to 2. And this particular case, we're going to have to be quadratic and the square root of x, or x to the 1/2. Right. So these are just samples of equations that are quadratic in form. Okay, so you have, remember, nth root of a to the m goes hand in hand with a to the m over n. Okay, so if I have like the square root of x, it's like the second root of x to the first. So you have like x to the 1 over 2. That's where that comes in. Yeah, so with square roots, you don't typically see the index number in many publications. So square root of x, you have like this second root of x to the first, like n is at 2, m is at 1, and then translating in terms of a non-integer exponent, whereupon we have a to the m over n. This can be x to the 1 over 2. Right. Now, where we have just crossing over, say if we're looking at solving for x, in the case of equations that are quadratic in form, and we'll say that we have x to the 4th plus 3x squared minus 4 is equal to 0. So this particular equation, again, okay, just like the first example, you had to be quadratic in x squared. Okay, so for x to the 4th, now we can factor this. Okay, just like x times x goes to x squared, well, we're going to have x squared times x squared will go to x to the 4th. And for factors of -4 whose sum or difference will be on the plus side at 3. So here we're going to have a plus 4 and a minus 1. Okay. Now, we can start factoring. Okay, now x squared plus 4. Now, a sum of squares cannot be factored. Now, with x squared minus 1, it's your option whether to factor it or not. But for x squared minus 1, this is a difference of perfect squares, so that one can be factored to x plus and x minus 1. And with using the zero product property, okay, so if I set each of the factors to 0, so if I have x squared plus 4 equal to 0, and I look at isolating the x squared term, so we have the x squared is equal to -4, and with the square root property of equality, so if I go from x squared to x, we have equal to plus or minus, okay, the square roots of -4, and in compact terms, okay, so x will be plus or minus the square root of -4, so the square root of -4 becomes 2i, so you have positive and negative 2i for this set, and for the other factors we have an x with x plus 1 and x minus 1. If I set equal to 0, okay, so if I set x plus 1 equal to 0, okay, so I have the x is equal to -1, and for x minus 1 equal to 0, I'm going to have the x is equal to 1, and so we have for our solutions in x, okay, so we have, again, so you have 2i, -2i, and we have negative and positive 1. Okay, so you have two complex solutions with 2i and -2i, and two real values in the solutions with negative and positive 1. And let me mention here for what we had here with x to the fourth. Okay, now especially if the equation is a conditional, with the degree of the variable being 4, this means you could have possibly have 4 solutions, and we did in this case with 2i, negative 2i, as well as negative and positive 1. Now, another case of an equation quadratic in form, but that has only one variable term, and I'm just going to keep this in fourth degree, and we'll say we have x to the fourth minus 81 is equal to 0. Okay, so in the higher degree in the variable, okay, x to the fourth minus 81, this in its own capacity is a difference of squares. Okay, because here we have x to the fourth would be like the square of x squared. 81 is the square of 9. And so I could factor what I have here to x squared plus 9 and x squared minus 9. Okay, and now I'm just going to mention now, okay, notice I could not factor x squared plus 4, but I could x squared minus 1. I'm just going to mention, okay, so with sum of squares, this one is not factorable. And in terms of what we have with x squared minus 9, because we have a difference of squares, that one is factorable to like x plus and x minus 3. But what I'm going to do here in the follow through is that I'm just going to apply the square root property of equality for both sets of terms. Okay, so if I go ahead and set both of these equal to 0, so I have x squared plus 9 is equal to 0, and I have x squared minus 9 is equal to 0. And if I isolate, okay, the x squared terms, okay, so for x squared plus 9 is equal to 0. If I take 9 away from both sides, so we have the x squared is equal to negative 9. And we have with the square root property of equality, so we have x equal to plus or minus the square root of negative 9. And so in this case, we have x will be equal to plus or minus 3i. And if I, instead of factoring, if I just went ahead and set x squared minus 9 equal to 0, okay, so I can isolate the x squared term upon adding 9 to both sides. So we're going to have the x squared is equal to 9. So we're going to have the x equal to plus or minus the square root of 9. So we have x equal to plus or minus 3. Okay. And so we're going to have yet another set of 4 solutions. Okay, so we have, in this case, right, so we have x is equal to negative and positive 3i. And for x, we have positive and negative 3i. So you have another quartet of solutions, 2 from the real number system and 2 from the complex. And tell you what, in looking at solving for x, I'll give you just some cases here, and we'll say we have for the first, okay, if I have let's say, I'm just going to keep these in fourth degree. Say if I have x to the fourth, and I say I have x to the fourth plus 2x squared plus 1 is equal to 0. Then I'll say I have for the next, and we'll have irrational roots in the mix. We'll say we have x to the fourth plus 6x squared minus 16 is equal to 0. And let's say if we have also for fourth degree in x, we'll say we have x to the fourth minus 16 is equal to 0. Okay, tell you what, if we go ahead and look into these equations again, we have all of these are fourth order in x, so we might possibly have 4 solutions, but no guarantees. Okay, now for the first one, we have x to the fourth plus 2x squared plus 1 is equal to 0. And this equation, okay, that is going to be quadratic in x squared. And this trinomial can be factored. And what's going to happen here is that for x to the fourth plus 2x squared plus 1 is equal to 0, this will be a case of a squared trinomial, okay, where this would factor out to x squared plus 1 times itself is equal to 0. So x squared plus 1 is going to repeat. So that means that from x, whatever we have from x, it will come exclusively from setting equal to 0 the expression x squared plus 1. Okay, so you have x squared plus 1 is equal to 0. And if I isolate the x squared term, so upon taking 1 away from both sides, okay, so we're going to have the x squared is equal to negative 1. And we have with the square root property of equality, so we have the x is equal to plus or minus the square root of negative 1. And so we're going to have the x is equal to plus or minus I. Okay, and so instead of having 4 solutions, okay, I have only 2 solutions, and both of these are in the complex domain with positive and negative I. Okay. Now for the second problem, we have with x to the fourth plus 6x squared minus 16 is equal to 0. And here I can factor x squared plus 6x squared minus 16, okay, to x squared. Okay, so we have a plus 8. We have times the quantity of x squared minus 2. And I have is equal to 0. Okay, so again, 8 times negative 2 is minus 16. And in terms of adding and subtracting, we have an 8 and a negative 2, where we have at positive 6 left standing. Okay, and if I set each of these factors to 0, so if I set x squared plus 8 equal to 0, and I isolate the x squared upon subtracting 8 from both sides, so I'm going to have the x squared is equal to negative 8, and again utilizing the square root property of equality, so we have the x is equal to plus or minus, okay, okay, the square root of negative 8. And right now we have x equal to plus or minus the square root of 8 times I. And the square root of 8 is not a perfect square value, but it can be reduced. So again, we have the square root of 8, and we have equal to the square root of 4 times the square root of 2. And so for the square root of 8, this will be reduced to 2 times the square root of 2. So for the complex number solution set I have for x, and we have plus or minus 2 times the square root of 2 times I. And in the notation, you could have the I, you can't have the I in front of the radical. Okay. All right. Now, for what we have in the case of the third item, okay, so we're back to a difference of squares, where we have a raised order in x. Once again, we have x to the fourth. Now, for x to the fourth minus 16, okay, factoring, we're going to have x squared plus and x squared minus 4. Again, I have is equal to 0. Now, from the example before, when I had x squared plus 9 and x squared minus 9, I said x squared plus 9 was not factorable. X squared minus 9 was factorable, but I decided to go ahead and work with the square root property of equality for both. But for what I'm going to do here, okay, now x squared plus 4, that expression cannot be factored into real integer coefficients. But for x squared minus 4, I think I'll go ahead and factor this one. So you have x plus and x minus 2. And if I set each of the expressions to 0, okay, so we have x squared. So I have x squared plus 4 is equal to 0. And if I take 4 away from both sides, so we have x squared equal to negative 4. And going from x squared to x, so we have plus or minus, okay, the square root of negative 4. So we have x at plus or minus 2i. And for x plus 2 and x minus 2 equal to 0, okay, so if I respectively take 2 away from both sides and adding 2 to both sides, for x plus 2, okay, so we have the x is equal to negative 2. And for x minus 2, I'm going to have the x is equal to 2. So I have x equal to 2i, negative 2i, as well as negative and positive 2. Yeah, so in this one, okay, we have a fourth order equation, okay, that again is going to land at 4 solutions. And before I get too far ahead, I just have to notice, yeah, for x squared minus 2 equal to 0, so you have x squared minus 2 is equal to 0. And if I add 2 to both sides, so we have that x squared is equal to 2, and we have with the square root property of equality. Okay, so I have that x is going to be plus or minus the square root of 2. Okay, so we're going to have, just taking what we have now, I overlooked that. So you have for x, Okay, so for x squared equal to 2, have x equal to plus or minus the square root of 2. Yeah. So we have the square root of 2 as well as the negative of the square root of 2. Okay, these are kind of bring us back to those equations that have non-integer exponents. And we have, say, in number 92, okay, we have an equation in D, whereupon we have 3 times D to the 2/3 minus D to the 1/3, okay, and we have minus 4 is equal to 0. And if you notice, you have a 2-to-1 ratio between D to the 2/3 and D to the 1/3. So we can say that this equation is going to be quadratic in D to the 1/3. And just in terms of factoring, let me give you just kind of an analog to this. If I have something like 3x squared minus x minus 4 equal to 0, with the factorization, okay, so I have like 3x squared, 3 is a prime number, 3x squared would factor out to 3x and x. And then for the factors of negative 4, that will allow both the outside and the inside products in the FOIL to add up to negative 1x. Okay, so the factors of negative 4, there has to be a one right combination, whether it's plus 1 minus 4, plus 4 minus 1, plus 2 minus 2, minus 2 plus 2. There has to be that right combination where the outside and the inside products will add up to minus 1x. And the only combination here will be plus 1 and minus, let's see, no, think about another set. Okay, so that is going to be minus 4 and plus 1. So you have 3x squared plus 3x minus 4x gets us to negative x. And negative 4 times 1 is negative 4. Now, instead of x or x squared, I have d to the 1/3 and 3d to the 2/3. And if I apply the same coefficient treatments over here, okay, so instead of x's, I'm going to have d's to the 1/3. So I have 3d to the 1/3 minus 4. And we have times the quantity of d to the 1/3 plus 1. Okay. All right. So just think of like d to the 2/3 is to x squared, is d to the 1/3 is to x, and just factoring. So these are analogous to each other. Now, with these factors, I can utilize the zero product property and set each of the factors to 0. So we have in the first, I have 3d to the 1/3 minus 4 is equal to 0. Along with setting d to the 1/3 plus 1 equal to 0. And if I isolate the d to the 1/3 terms, so we have adding 4, say in the first case, and here we're going to have 3d to the 1/3 is equal to 4. And if I isolate d to the 1/3, so we have upon division by 3, so we have d to the 1/3 is equal to 4/3. Now for d to the 1/3, okay, if I translate from exponent to radical, so d to the 1/3 is going to be the cubic root of d. And we have that the cubic root of d is equal to 4/3. And if I take the cube of both sides in order to translate from the cubic root of d to d itself, Okay, so the cubic root of d to the third, so this will become d, and 4/3 cubed, you got 4/3 times itself, and this will be 64 over 27. Okay. Now for d to the 1/3 plus 1 is equal to 0 for this factor. If I take 1 away from both sides, okay, so I have d to the 1/3 equal to -1, and if I translate into a radical, so d to the 1/3 is like the third root of d to the first, so I have the cubic root of d is equal to -1. Now, if I had an even root, like square root or fourth root, I would have no solution. But in the case of an odd root expression can reduce to a negative constant. So I can continue. And we have, upon cubing both sides, we're going to have that d is equal to -1. So for this particular equation, okay, there'll be two solutions, one at positive 64/27 and the other at -1. All right. Now, in taking what we have with 94, so you have another set of fractional exponents. Okay, so I have n to the 1/2 plus 6 times n to the 1/4 minus 16 is equal to 0. Notice between 1/2 and 1/4, 1/2 is like 2/4, which will be twice the degree of 1/4. So this equation is going to be quadratic in n to the 1/4. And just on a parallel note, okay, so if I have like the trinomial, say I have x squared plus 6x minus 16. Okay, I'll have factoring, so I have like x plus 8 and x minus 2. Okay, and we say that x squared correlates with n to the 1/2 and x correlates with n to the 1/4. So just kind of analogous to this factorization, but in the case of what we have for the degrees in n, so while it is otherwise x plus 8, I would have translated out to n to the 1/4 plus 8, and I have times the quantity of n to the 1/4 minus 2 is equal to 0, and then setting each of these factors to 0. So with these factors, okay, so we're n to the 1/4 plus 8 is equal to 0. If I take 8 away from both sides, so we have the n to the 1/4 is equal to -8. And writing from non-integer exponent to a radical. So we have that the fourth root of n is equal to -8. And if you notice, okay, we now are back to an even root radical. And I'm trying to say that the even root radical, in this case, the fourth root of n is equal to -8. However, since I'm dealing with an even root radical, the principal square root rule is going to kick in, where the even root of an expression cannot reduce to a negative constant. So for this particular portion, okay, there's going to be no solution. Now for n to the 1/4 minus 2 is equal to 0. If I isolate the variable expression, and so we have, upon adding 2 to both sides, So I'm going to have n to the 1/4 is equal to 2. And here I'm going to have the 4th root of n is equal to 2. And then freeing up n, okay, so again I can have even root radical to reduce to a positive constant. And here I can follow through and eliminate the radical upon taking both sides and raising to the 4th power. Okay, so we have on the left hand side I have n and 2 to the 4th. I got 2 times itself times itself times itself, and so this will come out to 16. So for this equation there's only one solution, and that is going to be with the number 16. All right, and we will continue looking at equations that are quadratic in form, as well as some that will have integer exponents, others which there will be none. And now, and again, we will get back to those, but for what we have now, and just crossing over to something that is, I guess, kind of an old topic, but will kind of segue over to, I guess, a new domain, and this we have right now in inequalities. Again, your inequalities are your statements like, not in the sense of not equal to, but like less than, greater than, less than or equal to, greater than or equal to. And there are types of ways upon which you can express inequalities. And we'll say we have, for instance, okay, if you have an inequality such as x is greater than 2, and if I were to express what I have here in terms of a number line, so we have in the case of x is greater than 2, if I were to display graphically, okay, so for x is greater than 2, okay, now on the graph, now the book has it as parentheses, but in Alex, instead of parentheses, you'd be looking at holes or open circles. Okay, so on the 2, okay, we have an open circle, meaning that because you have a hole or an open circle, 2 is not included in the description. But for x is greater than 2, representing x will be those values to the right of 2. And so I'm going to have an array that is going to go out to the right. Okay, so this would be like the graphical display of what we have for x is greater than 2. And just taking what we have in interval notation, and the interval notation you would have with parentheses and brackets. Okay, so 2 is not included. Anything that is not included among the finite values, you're going to have a parenthesis, and going continuously to the right. So you're going past 6 and going continuously increasing where we have approaching infinity. And let's say if we have another inequality, and we'll say that we have in this one, okay, we'll say that we have x is greater than or equal to -1. Okay, So just representing what we have here for x is greater than or equal to -1. Okay, so we have here for -1, the equal sign indicates that -1 is included. So we have a close point on -1, and the rest of the values x will be greater than. So again, you'll have activity going out to the right. Again, we have with interval notation. Okay, we have activity going in the same direction. Now, -1 is included, and this number is going to be in the brackets. Okay, now let's say we have a little bit of a change up in terms of the direction. And let's say we have that x is less than 0. Okay, so for x is less than 0, so we're going to have an open circle on 2. And for less than, we're going to have a ray that is going to go out to the left. Now for the interval notation on this one, if we read in order from left to right, so your leftmost you have continuously decreasing. We have approaching negative infinity, and then the upper limit you're looking at approaching but not including 0. So the 0 remains in the parenthesis. And let's say that if we have say for the remaining one direction inequality, if I have that x is less than or equal to 5. Okay, so for x is less than or equal to 5. Okay, so equal sign indicates that 5 is going to be included. 5 is going to be a close point, and then for the less than portion, again, we're going to have a ray that is going to go continuously out to the left. And for the interval notation, so again, the leftmost extreme, we have negative infinity. And then we have the maximum you have going up to and including the number 5. So 5 is going to be in the brackets. Now, let's say that if we have x to just simply be the set of all real numbers. So for what this is going to mean is that you're going to have continuous activity from end to end. So you're looking at the irrational numbers, rational numbers, all the fractions, decimals, positives, and negatives, as well as the zeros. So everything is going to be boundless. So for the interval notation, for what we have for the set of all real numbers, to the left, you have going endlessly to negative infinity. To the right, you have going endlessly out to positive infinity. Now, we'll mention, you're going to have parentheses around both negative and positive infinity, because think of like the infinities as endless activities. Think of it like an expanding universe. It never theoretically never stops expanding. So just think of like the infinities, negative and positive, being stretched out continuously, so they'll never come to a final resting place, thus no brackets in the notation. And let's say that, okay, so we have, again, one direction inequalities in the first four cases, and you have both directions continuously with all real numbers. But let's say that if we have discontinuity with both the lower and the upper limits, and let's say if we have something like a compound inequality where we can state that something like -3 is less than or equal to x, which in turn is going to be less than 4. Okay, so you have -3 is less than or equal to x. Okay, so for -3, now in terms of whether I'm going to have an open circle or a closed point, the equal sign in the descriptive statement where we have -3 is less than or equal to x, this is signaling that -3 is going to be included, so that is going to be a solid point. Now for x is less than 4, notice we do not have an equal sign, so we have on 4, we're going to have an open circle. And then everything in x is going to lie in between. So for what we will have this time around, instead of having an array or a line to run continuously, we want to have a line segment. We're going to have a starting point and essentially stopping threshold. And for the interval notation, okay, so we have going from and including -3, approaching but not quite including 4. So we have, since -3 is included, we're going to have a bracket. Since 4 is excluded, we're going to have a parenthesis. So I guess you can say that the most we have here, so you have starting exactly at -3, and you have going out to like 3.99999, but never exactly getting to 4. Okay, so these are samples of what we have with inequality statements. And for what we have in the case of section R8, okay, we have not only inequalities, but those that will make reference to what we have with absolute value inequalities. And just again with absolute values. Again, we're pretty fresh off of the absolute value equations. And sort of tying in together what we had with the equations. And again, if we have that k is a non-negative value, and okay, so just again, just tying in what we had with equations. If we have that absolute value of x is equal to k, then x is equal to plus or minus k. So we have two specific values with k and negative k. But if you're looking at a set of values, okay, and let's say that if we have crossing over to the inequalities, and if we have that the absolute value of x is less than k, if the absolute value of x is less than k, then what's going to happen here is that it's going to be kind of like a squeeze plate. Okay, so you have, again, by definition, absolute value is the distance away from 0. And if the distance is less than k number of units from 0, then your values of x will be between negative and positive k, such that negative k is less than x is less than k, and your interval notation would be like parentheses around the negative and positive k. And if we have that the absolute value of x is less than or equal to k, except for the equal sign, you're going to have history by and large repeating itself. So in this case, you're going to have that negative k is less than or equal to x, which in turn is going to be less than or equal to k, and your interval notation would be, say, brackets around negative and positive k. Right. So you have the same, pretty much the same mode of behavior whenever we have the absolute value inequalities to have less than or equal to k. But now if we sort of go beyond this particular scope and say we have that the absolute value of x is greater than k, what's going to happen here is that you're going to have sort of branching out two separate modes of activity. If you're increasing the distance away from 0, you're either increasingly negative or increasingly positive. So for what we have here, you're going to have that x is either going to be less than negative k, or it's going to be that x is going to be greater than k. And how would this look in terms of interval notation? Well, what would happen here is that you would have, for less than negative k, you would have like from negative infinity to negative k. And at the other end of the spectrum, you have going past k on out to infinity. And just for this particular symbol here, okay, this is going to refer to a union of sets or elements or intervals. And if we have, let's say, that the absolute value of x is greater than or equal to k, then you're going to have that x is less than or equal to negative k, or x is greater than or equal to k, and the interval notation to have from negative infinity approaching and including negative k. So the negative k is going to be in the brackets, and you got the union with the other, or the upper half set, where we have going from and including positive k, going all the way out to infinity. Okay, so these are the possible cases that exist for what we have here. And let me just give you a couple of cases where we have absolute value inequalities. And let's say we are looking at determining the interval solutions. And we'll say we have a statement and we'll say that we have the absolute value of x minus 1 is going to be less than or equal to 7. Okay, so we have the absolute value of x minus 1 is less than or equal to 7. Okay, and so let me Okay, so for your cases here, okay, so for the absolute value of x minus 1 is less than or equal to 7. So you have the absolute value term by itself and the constant on the other. Now k is at 7. 7 is non-negative. And the absolute value of x, again, we have represented by the absolute value of x minus 1. And in terms of how these quantities relate, okay, this statement, this is going to apply for the third case. Okay, so looking at solving for x, okay, so I have the absolute value of x minus 1 is less than or equal to 7. Again, your k value is at 7. So if this is true, then what's going to happen with x minus 1, once you take out of the absolute value notation, it will be sandwiched between negative and positive k, or in this case, between negative and positive 7. So we have that negative 7 is going to be less than or equal to x minus 1 which in turn is going to be less than or equal to 7. And again, I'm still looking at solving for x. So to get x by itself, what I'm going to do is I'm going to add 1 to all sections of this compound inequality. So we have negative 7 plus 1. Okay, so this is going to be negative 6. And in turn, we have negative 6 is less than or equal to x. And x in turn is going to be less than or equal to 7 plus 1, which is going to be 8. And if you notice the case, so we have negative 6 is less than or equal to x is less than or equal to 8. So for the interval solution, okay, for x, okay, we have from and including negative 6 as indicated by the equal sign. So you have negative 6 less than or equal to x. X in turn is less than or equal to 8. So guess what? 8 is also included, and there will be a bracket around this one. Okay, so that would be the interval solution for this particular inequality statement. And if I have, let's say, and I'm just going to keep the absolute value of x minus 1. And if I have that, the absolute value of x minus 1 is greater than 7. So I'm keeping the k value at 7. And this time for the absolute value of x minus 1 is greater than 7. Okay, this will be a case of the absolute value of x is greater than k. And in terms of what to do with x minus 1 once I take it out of the absolute value notation, well, we're going to have these two types of statements to abound. Okay, so x is less than negative k. This will translate out to x minus 1 is less than negative 7. Or it could be where x is greater than k, which would translate out to x minus 1 is greater than 7. So for what we have in the solution sets, if I isolate x in both cases, so I have adding 1. Okay, so for adding 1 here, okay, so for x minus 1 is less than negative 7, x is less than negative 7 plus 1, so we have that x is less than negative 6, or it could be at the other end of the spectrum that x is greater than 7 plus 1, and so we're going to have that x is greater than 8. And just taking what we have with these statements, if I display an interval notation, okay, so for x is less than -6, so we have going from negative infinity, approaching but not including -6. We have or, and so we have symbolized by the union with the other set, which we have in x is greater than 8, and the interval notation for this second half will be have a parenthesis around 8. Then we have going all the way out to approaching infinity. Okay, and so that would be the interval solution for this particular inequality statement. Okay, and just some items to mention. Okay, again, so that U symbol again refers to the union of intervals or set.